So, reliability. Last big chapter, and this is all what we will address in that field. First, terminology. How do you describe, what terminology do you have to describe a dependable system in engineering? What terms are you using to describe that? Dependable system in engineering. Robustness.
Error rate or...
Error rate? Yeah. What's error rate? How do you define that?
Some sort of like average that you'd use to say, I expect this to fail after this much time on average.
Yeah. Anybody knows the technical term for that? Mean time between failures, exactly. That's what you read on the data sheet of hardware components, mean time between failures. Exactly. For larger systems, this is actually also calculated. You have mean time between failures for systems like nuclear power plants or for airplanes. You can actually look that up. You can look up what statistical chance the engineer gave you to build the whole thing. How often that thing is going to explode. And fancily enough, for some nuclear power plants, this is orders of magnitudes more likely than the plane crashes. Admittedly, it's still a relatively small number, but a lot larger than for many other systems. So, here is where we start from. Term reliability is technically actually quite nicely defined. It's some form of a measure of the deviation between your actual system and the specification. Can you quantify that? Can you measure that? That's my specification. That's my system. There's a delta here. That delta is called reliability. If you have 100% overlap, 100% reliable system, otherwise you measure it like that. Right? And it also gives you the first hint on where the actual problem is in all of this kind of terminology. It measures against the specification. So if the specification says my airplane has to crash every 5 minutes, you have a 100% reliable system in an industrial definition of the whole thing. Okay. Then the next lineup is important in terms of how we express that. Failure, error, and fault is usually not used in a clean way. It starts with a fault, or what you would call a bug in a software system. The fault is the actual reason why something goes bad. But the fault in itself is just a fault in the system. It does not necessarily lead to any trouble. But if there's a fault in the system, you have, for example, many faults in your software systems everywhere. Most of them are just simply staying undetected because they never triggered anything. They're just dormant in there. And sometimes some cybersecurity person finds them and exploits them, and then they do become a problem, but often they're quite dormant. But if the system gets into a state which is deviating from the specifications, that's the error state of the system. Right? Now you begin to be in trouble. And then the failure is the actual deviation from its specification. Okay. What are the most frequent sources for faults in our practical complex systems? What's most likely to fall over? User. Classical engineering answer. Why do we have users? That's a correct concept. Nobody should ever have invented that. The user. Yeah, but just on the system itself, what is the most likely after the user pressing constantly the wrong button? What is most likely the source of failure in your complex systems? Software?
Outside intended environments.
Used outside the intended environments, which is a specification failure. Right? Yeah, which is a specification failure. If you say, my system is specified to work underwater and you throw it in space, that's a specification fault. Well, okay, you can throw it at the user and you didn't read the specifications. Sure, okay. That's one way of looking at it. What is commonly perceived as the most likely source of failures in our complex systems? If you read in the press something happened to an airplane, for example. Yeah. It's usually quoted as there was a mechanical error, or which is a summary term for something went bad. It doesn't mean that anything bent or something like that. And in public perception, this is usually what happens. A piece broke, some piece of metal didn't quite hold up, some mechanical system, some electronical system broke, the computer crashed because the CPU melted or anything like that. And while this of course happens, this is, statistically speaking, by far the rarest occursion of these faults. And it's not only rare, interestingly enough, they are also mostly predictable. How frequent a CPU is actually going to melt, or when a CPU is going to melt, you have some physical idea about this. This is not a random combinatorial explosion of things. It's actually much more simplistic. How often a component fails, how long a gyroscope works until it actually begins to do something bad or until it breaks. You have a fairly good statistical distribution of that one. If you're not happy with the statistical distribution, if you say that, well, there is still a chance, I plug it in, it goes poof. You buy a bunch of them. And you can very quickly get the statistical distribution of all your dependencies down to a level which is somewhat identical to impossible. If you have enough systems, and you know that each of these systems has an average time between failure of a few million years, and you use 10 of them, you just have to guarantee that all 10 of them are actually failing before your system goes down.
So what you're saying is my aircraft should have 10 computers on it, all in stack.
What should have more computers on it?
What was it?
What was yesterday? I didn't hear.
Sorry, my aircraft should have 10 computers on it. And they're all back.
Yeah, and your aircraft does have 10 computers on it. Actually 9. Yeah. We will see whether this is easy or what we have to consider to get this done, because just having 9 computers side by side doesn't solve anything. You still have to get this in a sensible way. And the other very frequent source of issues are actual configuration and specification problems. That people use it in the wrong context, user error, wrong specification, or that plainly the specifications are wrong. And how do you make sure that your specifications are sensible? You as an engineer get a sheet of paper with the specifications on it, you read through that, I don't know, let's just do it. Or what do? What can you do to a piece of specification? Is there anything you can do to harden that? Say again? Test the specification against what specification? So
take the system, take the specification, run it, and see if it performs.
Yeah, but you can only measure against the specification. So you're saying basically you're using common sense. You're running against the specification and look where that thing flies. If it doesn't fly, there must be something wrong with the specification. Maybe. If you don't find a flaw in the translation from the specification to the actual system, well, maybe it's misspecifications. But you can actually do something. Some sort of logical verification. Yes, against what?
Against, make sure that at least all the specifications are consistent.
Yes. Yes. So that's the first step. Do my specifications contain contradictions? And this you can actually logically test. If you can formulate your specifications in some kind of a logical sense, then you can check for inconsistencies and contradictions in the system. That's at least something. So you know that the specifications say if my car goes on the right lane, sometimes it goes right, sometimes it goes left, because you find in different parts of the specification different definitions how this is to be done. Right? But that means you need to translate your specification into logic, which is another big source of problems, because you translate your specification into logic, and then you go back to the original guys who actually gave you the specifications. Is this what you want? And the guys look at your logic massacre and go, I don't know. I want the thing to fly. What you defined here, I don't know whether this is actually useful in any way. So what can go bad in terms of in the logic domain? 3 categories. First one is non-termination, not in the sense of functional programming environment where we have termination or not, but in the sense of is it actually delivering stuff on time? So non-termination, overrunning of deadlines, violating any kind of timing constraints, all that is non-termination. Range violations and other stuff which can be detected by the runtime environment. So runtime violations of your type systems, of your definitions which you have given to that one. It's another class of violations. And the last one is simply, it's still inside my specifications, inside my language, but it's simply the wrong value. So you want to be on a certain flight level at the moment, but that doesn't mean that this is the flight level which you are supposed to be. You're here because I extended the deadline? Or you're just late? You're just late. In the time domain, we have 3 possible options what can go wrong in time. Transient, intermittent, and permanent. Which of these faults do you want for your system? Permanent. Permanent? You don't want any of them. But if your system occasionally shows any of these things, if you have a permanent fault, that makes your life, in most cases, a lot easier. Because the thing died, and it stays dead, and you can do a post-mortem on it, and you can go through the logs and see what's going on. This is from a analysis perspective what you actually want. Intermittent faults, this is the stuff which is designed to annoy you. Intermittent faults are always happening roundabout when you're still in your PJs at 5 o'clock in the morning. So there's some alarm tick going on some of your servers, and every time you get out of your PJs and you get to the actual plant, the thing is gone again. Those intermittent faults, it's on the blink and doesn't do and come back, are a little bit more annoying. And the other one, completely random glitches. Every once in a new moon, your system goes a bit and then continues smooth and straight on. And if you have blinked, you didn't even notice it. That's very, very annoying. Glitches. Did I tell you about one of my helicopter glitches which I debugged a few years back here? Running helicopter experiments, and every once in a while, one of our really big and chunky ones, one of these meter 50, meter 60 machines which are easily taking your head off, in mid-air when the swash plate was just moved all in the same direction for a few milliseconds and then came back to normal flying. Now, if a machine of this kind of energy gives you a short swash plate twist, that sounds intimidating. It's not a reassuring feeling if you see that your whole airframe is just getting a brief shock, and then the thing stays there like nothing happened. So of course you take it down and you try to analyze the logs, you see what's going on. How do you debug that? Where do you start? Where do you suspect the bug to be? You're trying to replicate the conditions, so you just fly it again. That's what I've done. Flew it again. Nothing happened. Take it down again. Flew it again. Took it down again. Didn't learn much. I learned it occasionally happens. And I also learned I don't want that. Where do you start now debugging? Refactor? How do you do that practically? You just rip out everything and just replace it module by module? What could it technically be? Just asking your physics background, your computing background, your engineering background, your electronic background. What can cause that?
Could be a timer thing, could be something with controls, could be something electronic, could be code.
Cosmic breach.
Could be the radiation if you're working on it. I would say it's probably
Electrical interference. Yeah.
Operating next to a
Yeah. Things you didn't enumerate yet. Power supplies. That you have issues with the stability of your overall power supplies. Electrical interference. Yeah. What would your gut feeling tell you is the most likely? Where do you start? You have to start somewhere. Say again?
I just realized kind of the worst case handling. So is trying really hard to do something.
It's trying really hard to do something, so a software fault. So your theory is on a software fault at the moment.
So you said suddenly supply itself extra power or
like sending a command out of range.
Range overflow. Someplace rolls over. Okay. This is the easy stuff. So you check your software, you double check your ranges, you make sure your controller is not gliding away, not having an overflow anywhere. That's the first thing you check. Okay, tick, done. That's fine. That is not the issue. Next.
So presumably you have some sort of control which is sending commands to
Yeah.
actuators.
Yeah.
Something like record that.
Yes, and I did. And there was no transmission fault. There was no fault in this command. The commands were all correct.
So the problem is that you're recording the server.
The problem was what?
Were you recording the commands?
Well, the commands in terms of the electrical signals.
Yeah.
Yes, and those electrical signals were fine.
So
On the sending end or the receiving end?
On both ends.
So the signal was getting to the actuators.
Yeah, yeah,
Stack.
yeah. You have to be careful because what you actually measure here is the signals with respect to ground.
Yeah.
Yep. Okay. So the next thing is you're checking your power supplies and to see that your ground levels are stable, that nothing is actually spiking on the ground level there. Nothing's happening there. So you rip out the power supply, get a new one in. Then you begin to suspect mechanical faults in the servos, in the controllers of the actual motors of the whole thing. Okay, so servos out, new motors in, new controllers in, still there. You begin to suspect the actual power source, easy, battery out, completely new battery model in, nothing happened. Okay, you get desperate. You rewire the whole thing because you expect that maybe there is some breakage somewhere which you don't know. Rewire it, nothing happens. Still there. Then you actually kick out your controller. You kick out your computer, get a new computer in, replace that one, still happens. Then you start changing your motor because you think that maybe the motor has produced some electrical interference. We're talking about something around the ballpark of 120 amps going to these motors, so this is pretty beefy stuff. This is way beyond what goes into your house, for example, so this is fairly energetic systems. So you just change the motor in case that there's something out of whack in there, still there.
Was the hardware connections like?
The hardware connections. Ah, good point.
What's flat?
Yes, but we are not amateurs on that side. So of course that's the first thing you check, that all the connectors are actually solid, nothing is wobbly there, and you actually resolder stuff, and you make sure that this is not a question of some connector vibrating anywhere. This would be a bit amateurish to have that. No, we are usually not designing systems like that.
The point that you could build an entire helicopter with all the spare parts that you take on the
Yes, and I could have almost, yeah, but I used another one, which was a similar model, and didn't do that.
Did you try to downgrade things to
Downgrade? Well, making a helicopter hover is a pretty downgraded operation. So if a helicopter doesn't hover, it's not much of a helicopter. There's not much to downgrade below that point. Okay, now I give you a hint. Then I flew this thing not only in Canberra, I flew this thing at the coast. I flew this thing somewhere else. It didn't happen anywhere else. It only happens in Canberra. It didn't have a GPS receiver. So it didn't know it was in Canberra. Something to do with the altitude, yeah, but no. It was not the altitude. Interference. Canberra has a weird radio station of some sort. No, it was not that either. Keep guessing. Weather conditions? Yes. What kind of weather conditions do you have in Canberra? Very dry.
Static buildup.
Ah! Static buildup. Because after a week of testing that thing, I then witnessed, out of pure coincidence, a pretty large spark going over the gyroscope of that thing. And that gyroscope, of course, measures the whole positioning of the whole thing. The gyroscope goes a bit... And that only happens in Canberra because it was dry enough for the mechanical parts to build up enough static charge that you have those kind of discharges over the whole thing, which only happens in desert environments. Only happens in those kind of places.
You said there were no anomalies going to the server.
It's not an anomaly in that sense. That glitch is actually a spark which is of such high voltage that it affects the whole system in a way which you cannot really measure on the data lines in a sensible way. It's very short, very high energy, and doesn't really turn up on these on any kind of a lock which you have on those systems. So I don't know where it went. Maybe I wasn't doing the lock right, but I didn't see it on the locks anywhere. This kind of holistic debugging, that you have to understand the whole environment of your system, including the weather conditions you're actually working in. You need to have a basic understanding of physics around the whole thing.
For such a high voltage spark, wouldn't you have heard any noise from it?
No. Well, this is a 1 meter 50 helicopter working in front of you. This needs to be very loud to go through that one. If you ever seen a machine like this in 10 meters distance or something like that, they're quite noisy. Even though this specific machine was actually a high efficiency asymmetrical blade machine, something which is a little softer, a little bit more silent than a normal helicopter. Normal helicopters have actually symmetrical blades for faster responses.
Do you know what model it was?
Say again?
Do you know what model it was? Sheer curiosity.
Whether I have a what of that?
What model it was? What sort of aircraft?
What aircraft? That was based on an extended version of a T-Rex 800, which is a 1 meter 60 rotor span machine. which we have been flying for a while. Unfortunately, it has been stolen, so don't have it anymore. The Brian Anderson building is the most broken-in building on campus, most popular, and we have lost lots and lots of stuff in that building over the years. Who would take a helicopter? Well, people who know how valuable these things are and how much equipment is in these machines. Don't hire PhD students who are stealing helicopters. Okay. You need to be, as full engineers, aware of all the physical constraints there. And I cannot repeat and emphasize this enough, how important it is to have some basic physics background if you do physical deployment of any system, because without that you would never have guessed that one. Actually, you're the first student ever who guessed that. No, it's not going to translate into another deadline extension now. Okay, so that's just a fancy, colorful diagram in categorizing which states you want to be in or not want to be in. The one thing which you can see from this diagram is there's also a category which is industrially categorized as fail uncontrolled. If you just have no idea what's going on. Something happened, something went bad somewhere, and you have no logs over it, you have no control over it. The thing just crashed and you cannot reproduce it, you cannot trace it, you have no idea what's going on. Okay. So, how do we do that? How do you build a system which is really reliable? Where do you start? What do you do with the design specifications?
You have to use these broad terms by definition. Like, I know it's funny, but
no, it is actually like that. And most of it is you start by just reading. You start by investigating, understanding the whole system as detailed as you possibly can. Don't go into your system design blindfolded with the idea of, well, I have my specs, go. You need to understand the context. You need to understand the details of your system. If you have hardware components, which you usually have, there's no way around reading up. Understand your hardware components, understand your sensors. You remember the chapter about sensor integration and how many things you can consider there. You just have to go through all that. Constraints of the underlying runtime system. Do you understand what you have in terms of the software side of things? What your runtime system actually provides. So, for example, the great question about the task switching context. Good question, to which I don't have a great answer, but at least my guess was 2 orders of magnitude faster than yours. Okay. First thing is fault avoidance. You try to build your system that you have the smallest possible number of faults in your system. And you do this on the hardware level as well as on the software level. Hardware components, consider environmental conditions. So for my bearings, for example, I did not consider the static buildup in certain weather conditions for those systems. Hardware design, that's something that is particularly alien for computer scientists, because the concept of, for example, putting little rubber support struts around your boards is not coming to their mind. That's not, because what can possibly happen? It lies on my desk. Right? The concept that your system is actually deployed in an environment which is usually exposed to lots of different weather conditions, to shocks, to vibrations. You deploy this thing as a motor controller, like in a car engine controller. Now, car engines are pretty readily highly vibrating kind of devices. And you strap a piece of electronics on the whole thing. You need to be educated and knowledgeable how to do that so that it doesn't shake the bits out of your thing in the process, that you can actually keep your PCB alive in the process. Is your PCB able to sustain the environmental conditions inside a motor compartment? It's not only wet, it's usually also greasy and oily and all other kinds of chemicals which are flopping around in engine compartments. You need to be isolating against that kind of stuff, because pouring a bunch of oil over your controller is probably not very, very healthy for it. And the other comment was very correct, very valuable. Connectors. Connectors is still one of the most dominant sources for failures. So if you look at statistical failures for hardware components, it's the exact opposite of what is commonly assumed. The by far most failing components are of two sorts: connectors and batteries. Those are the two weakest components of pretty much every kind of hardware design. That your battery chemistry is not holding up to what you think it does, or your connectors are wobbling. Now, how many connectors can you choose from if you design your system? Boy, there are companies which are doing nothing else, and they have tens of thousands of connectors available to you. Wouldn't it? I mean, I need a 5-pin connector. How many different possibilities can there be to design and buy a 5-pin connector? As there are a lot of different possibilities to do that. Why is it actually physically a problem? Why are connectors physically an issue?
Size, corrosion, conditions, strength.
Yes, but I mean, cables are not an issue, are they?
Yes, they are.
Yeah, okay. But not in comparison statistically to connectors.
Okay, yeah, okay, sure.
So why are connectors special?
Because all the inconsistencies that happen in that interface.
Mm-hmm.
So within, say, the core of your wire, you're going to have a fair amount of consistency end to end. Right?
You have redundancy in your wire, because your wire, you can, for example, put up a design out of many little wires, and they can all bend a little bit independently, and some of them break. Who cares? You have redundancy in there.
Connect is a single point about it, and there's so much that can go wrong to make a core connection, which then can have big
Yeah.
They have to be designed like strong enough and reliable enough to make a good connection, but also not over-engineered so they disconnect.
Yeah, they should also come apart at some point. Yeah. But if you're talking about electrical connectors, which mostly we're talking at the moment, it is just two pieces of copper or other metals making contact. And this is a point contact of some sort. Or you have it over a larger surface, but how do you do this is actually making contact over the whole surface. How much surface contact can you do there? You can have then conical connections where you have cylinders making contact. How do you do this reliably? And then you vibrate the whole thing. Does it actually lift off? You have springs in there usually. Springs which are keeping the contacts together. Are these springs bouncy? So when you close these contacts, are they going to bounce? When they bounce, what is happening at this contact? You spark. Now you spark at these electrical contacts, you spark often enough, it doesn't transmit anything anymore because it's just burnt down after some time. The absolute bare bone, trivial physics, is not hard to solve. And there is, of course, lots of engineering around fantastic connectors, and good connectors cost beefy money, which is also a constraint which you have to do in your design, because The connector in your board, which you use at the moment, is by far the most expensive component. Yeah?
Right.
The RJ45 connector. It's nothing but a 4-port RJ45 connector, right? But this is by far the most expensive component. It is way more expensive than your CPU. It's insane, right? But connectors are, and this is a cheap connector. It's the cheapest I could find. Sorry. If you want to have an industrially hardened connector of some sort, you're easily dishing out a few $100s on the connector by itself. Then, of course, it's a connector which has a nice screw-in connection, a nice relief of the actual contacts. It is weather sealed. It has nice gaskets around the whole thing everywhere. Gold-plated, of course, but it costs you a few $100s to do that right. And you can also, if you're an audio fan of some sort, you can also dish out any kind of money for plugs. Just simply super gold-plated, God knows what. Getting the stuff apart. You also need to have the ability, if it's, for example, a switch which connects a battery which can easily produce some 200 amps, you need to have a switch which can actually pull this apart without producing a big spark on the other side. Imagine you want to design switches which are capable to be used in a power plant. This is the opposite end of having little electrical connectors for low power. This is now high power connectors, but the problem there is usually it doesn't help you to separate pieces of metal. You understand why? Yeah. What you do is you just put these contacts apart, and you have a beautiful arc which is spanned from one side to the other. And you put this further apart, and the arc becomes larger, and you get a little scared. But it doesn't stop. It doesn't do anything. It's a nice light show, but even the current barely goes down in the process. What do you do? It's some kind of a fire extinguisher, basically, which is rigidly attached to the whole thing to actually do this over trying to kill any possibility in that switch to keep, try to. So these switches are insulated in a way that you try to you actively have to kill the spark in there, otherwise they don't disconnect ever. So connectors are a big source. The other thing is batteries, as I said. Which battery technology do you trust for your device? Do you have any idea about battery technology? Nickel hydride? Nickel cadmium. Does anybody remember what a nickel cadmium battery looks like? Yeah? Nope. Okay. You are too young for that, I think. So you are old enough to remember what a nickel cadmium cell looks like.
I think I used to use my use less now.
The reliability. Isn't it
Nickel metal hydride? Yeah.
I think it was more reliable.
Okay, to give you an example from a field which I'm familiar with. As you know, I'm a quite passionate photographer. And if you buy a camera which has been built in the 70s sometime, you look in the spec sheets, and the manufacturer gives you, this camera works down to minus 45 degrees. Ui, nice. Now look at my shittily expensive professional camera from today, which costs about 10 times as much as this camera from the 70s. And the spec sheet says you can use it down to 0 degrees. Really? That's the end of it. Batteries. Because, yes, you can use batteries down there, but manufacturers are hesitant. Because guaranteeing the performance is actually quite problematic. And you're perfectly right, nickel metal hydride is something which has been held up in professional photography for a long time for that reason. Because nickel metal hydride chemistry can actually be used at lower temperatures in a somewhat dependable way. They lose capacity, but lose it gracefully. They don't drop out, and you can use them up to -20, and it still does something. You can still shoot. You lose a lot of capacity, but you can still operate. While all the current stuff, nickel polymer, lithium polymer, and related chemistries, they mostly stop around 0 degrees. Below that, they're very unreliable. It's not great. On the other hand, the energy density in these systems, are you scared of batteries?
Yes.
Which batteries are you scared of?
I go with USB drones, so ones I use for that are really good fun when they go off.
Yeah, have you ever seen all these batteries here? Yeah. So you're all scared of the devices which are carrying around here. Yeah, of course. I mean, Samsung got kind of a press coverage with their batteries which they've been using there.
The raw energy is small pipe bomb.
Small pipe bomb, yeah, exactly. Putting it into the right casing. I optimized that a bit further with submarines. So you have a high pressurized tube which is solid enough to produce, to sustain some several thousand meter depth pressure underwater. So that's a pretty beefy tube. And then you pressurize this whole thing, and then you put a battery in there. So using this above water is actually an unpleasant operation with the imagination what that thing can do if this battery goes haywire. Have you ever personally experienced batteries exploding on you? Yeah?
Yeah, just like when you, I flew with some guys from drone racing, and the amount of times that it comes loose and hits the prop as it's coming out,
Sure.
and you go over to your drone and it's smoking, you disconnect it, you throw the battery away, and you just stare back. That's all you can do.
Sure. But you only saw it smoking, you didn't see it actually burning down.
No.
Also burning it down?
Yeah, it's like
okay.
it's a flame. It's a strong flame. Like
Okay.
you usually get to when it's smoking, you throw it away and
Okay.
you watch it.
But for drone racing, what capacity batteries do you have around about?
I think I was using 1600 milliamp hours, which is like small ones.
750 milliamp hours? 700 milliamp hours?
I think mine was 1600. I think it was
1600?
Yeah, I think so.
Okay, 1600. Okay, multiply this by a factor of 5-6 for larger machines, and then a whole chunk of the whole thing. The problem is that there is actually no fire extinguisher chemistry which actually stops that. I was talking to the fire experts here at the ANU about those batteries, and the general recommendation from the fire brigade is watch it burn down. There is nothing you can do about it.
I saw a YouTube video this morning of people trying to put out a fire in a Tesla car. They caught on fire, and it took them like 35 people several hours.
Yeah. Well, with cars it's different anyway, because the fire brigade almost always lets a car burn down regardless what battery it is, because it's way too dangerous for the guys to actually get close to that thing in case that there's another eruption of some sort. You just let it burn down anyway, which is not what the car owner usually prefers. You call the fire brigade, and the fire brigade just watches your car burn down.
Unless the surrounding trees and things that burn down.
Yeah, well, I don't know whether this was your intention when you called the fire brigade, that they protect the trees around your car. Yeah, but battery technology is... do we have any hope that battery technology is actually becoming safer or more energy dense? There are constantly press releases about more safe and more stable battery chemistries, but it's hard to do. And if they are starting to burn down, they usually nowadays take down quite a bit of junk around it. So there definitely have been whole houses being burned down because once these lithium polymer blocks, just the completely unprotected lithium polymer blocks which you have in little airplanes, they are unstoppable. There's nothing you can do about that.
It might just in my wardrobe.
Yeah. So, software side, formal methods. steer improvers, strict coding standards, and employs some, halfway reasonable runtime environment which is actually living up to your constraint. But I'm preaching to the choir here. That's something that you should have understood by now, how to do this a little bit on the software side. How do you find faults on the software side now? Lots of testing, team programming methods maybe, constantly changing codes, make the other guy test your own code all the time. This is done, which is actually quite frequently done. I'm also feeling a bit bad about not really training you guys for that, because code review is something that you experienced as this is a nasty thing which some lecturers do in terms of peer review and let other students look into your code, but this is annoying. And once you actually work in an industry where this is being done, code review is more than what you spend more time in code review than in ever actively programming. This is a very normal part of your processing. For that reason, this is the most productive way of actually removing faults. You're constantly reading other people's code and trying to give feedback on that. For real-time and embedded systems, there is quite an obvious limit to testing. Testing whether your thing flies. This is not something where you can find a lot of faults, because every time you have a significant software fault in your controller for something which flies, you just crash it and explodes. It goes down in flames, and that's about it. I was enjoying one of the Outback rescue teams a few years back. It was a combination between engineers and computer scientists who have been designing the whole thing. And the computer scientists were full in the mood of, we have to do proper testing. Let's design something and then we run it against tests and we see how it goes. And the engineers built the frame and the engine. There was a combustion engine in the whole thing. It was more the job for the engineering guys around that one, and the software, the computer scientists have done the navigation, the flight control around it. And the thing took off, flipped around, it crashed, and the engineers went, shit. The computer scientists went, hey, we learned something, cool, there's actually a bug in there, we found it. The engineers are looking at it. There must be another way. So there's only so much you can do in these high real-time, high integrity systems to find any kind of a bug. If you have a fast flying system of some sort, you have to do a lot of your things offline. You cannot actually test it. And the test space is just completely infinite from a practical perspective. This is way beyond just the combinatorial explosion you have. You can barely ever reproduce exactly the same situation twice in these environments if you go for full real-world deployment there. It's pretty complicated. So as we have been really trying hard to avoid any kind of fault in our system, there are still a few things left. One is, what do you do if systems are temporarily inaccessible or completely inaccessible? So you design your system and you know that there may be a few faults left, but it is not that you can send in the service team, because this system is deployed in an unreachable space. And this is a lot more than you think, unreachable spaces. Imagine, for example, the light controllers which are deployed in the roof of a big soccer stadium or a big football stadium. These areas of the building, of the design, yes, they're physically reachable, but this is expensive. This is a massive operation to send somebody in here to actually build a crane which can actually reach that ever again. You don't want to access that. A lot of systems will be deployed in places where you cannot just send somebody in, or they're in places where you don't want to go in the hot parts of a nuclear reactor. You don't necessarily want to go in there when something goes bad and just send the emergency brigade in there and repair the whole thing. You want to have these things a little bit more robust and tolerant. Well, I leave it to your imagination what I mean by remote and hostile environments. You can imagine a lot of these places. I don't mean guys shooting at you, but for example, if you want to deploy something which explores close to the crater of an active volcano, that's a pretty hostile environment. You don't ever want to actually be there. You just want to send your devices and your sensors in there. And if they go bad, you just push it into the volcano and get rid of it. You don't want to actually pull this thing ever out of there again. So I leave it to your imagination what that could be. Unmanned, unreachable. So fault tolerance. What can you do in terms of fault tolerance? First, we have to understand what options we have. Those are the three basic categories: fail-safe systems, graceful degrading systems, and full fault tolerant systems. Full fault tolerant, what does that mean? Something goes boom, and you don't notice. Continues as if nothing happened. Full fault tolerant system, just covers it up. Can you do that? Is that physically even possible? Yep.
The fact that the airplane has got 9 computers that are all running the same stuff, and then there's a version algorithm on them.
Yeah, but how do you switch over from a faulty component? Wouldn't there be a jerk or jump or some kind of a noticeable interference of some sorts?
Well, aren't they all always running the same?
Yeah, but somebody has to actually make a decision.
Something out of the ordinary, the rest just ignore it.
Yeah, but if you rip out a cable out of a system.
So, for example, a router, like if you've got a network configured and one of those dies, like you just stop receiving messages, and the messages that you would send to it just go to void, so no one knows it's actually submitted. Except the network might notice if it stops sending messages, stop getting where they go. Bad example.
Well, if you think about routers in terms of an internet router, then this will repair itself very quickly, but not in zero time. If you design a router for a real-time system, can you rip out a cable and the receiving side does not notice that you ripped out a cable?
Well, the systems that we've designed, like my design is very much capable of it.
So you need redundancy to even think about that. You have multiple physical connections and you rip out one of them. And if you designed your network distribution good enough, then there's not even a bit level jerk on the other side. And the packet which has been interrupted at some point in your physical device, in your physical connection, is just going at the same time through another path, and the receiving side doesn't notice that. So, yes, that is possible. Fault tolerant. Can you be fault tolerant for any number of faults? Obviously not. Once too much of your system burned down, there's just nothing left to fall back onto, because full fault tolerance is based on the concept of you have some redundancy, you have something to replace it with. If there's nothing left to replace it with, you're doomed. So full fault tolerant can only handle a certain innumerable number of faults, then you're down. And maybe you don't completely down, maybe you go down to the next step. You get to a graceful degradation stage, that you start powering down parts of your system, which is not the core functionality. So if your auxiliary power unit in your airplane goes down, you probably power down your board entertainment system first, before you power down your flight controllers. So you try to reduce functionality where it hurts the less, and you can still keep up base functionality. So graceful degradations usually to survival mode, to basic reflexes. And the last stage is fail-safe, and it means actually something quite different from what most people think it means. Fail-safe doesn't mean it's safe from failure. Fail-safe simply means that you fail in a coordinated and defined way. You fail so that you can come to a defined stop, have some nice locks around it, and you stop in a consistent state for your system. You can actually power it up again later. You stop your system in a consistent state. Now that's not a good idea for a flight controller, but for many systems that's of course a great idea. If you have a distributed database of some sort, you want to go down to some graceful degradation for some time, but at some point you want to fail stop in a fail-safe way with the whole thing. So this was just for definition. Hardware redundancy. Okay, now we have to actually talk about what extra hardware can you throw in to make your system more reliable, more dependable. More hardware for detecting failures. What hardware could that be? Many of your modules which you buy off the shelf already have a lot of this built in. You have overcurrent sensors and protection systems. Those are all hardware monitoring systems which are looking at your devices while the device works. Something goes bad, you get a signal to the outside, or it actually powers down by itself. That you can detect that. Additional hardware to handle exceptional situations. For example, additional CPU power to do that, or to have complete standby backup systems for the whole thing. Usual philosophy, avoid single points of failure. Can you do this? Can you, for example, build an airplane which doesn't have any single points of failure? What are single points of failure in an airplane which you cannot get around? Come on, you have two. The rudder? Yeah. It's actually quite macabre comment because a lot of airplane crashes happen because the rudder is actually gone. And people don't. The rudder is not something you really need that much, but the rudder is actually making you crash particularly if the rudder is stuck in the wrong position. You on a civilian aircraft, you have barely any chance to recover from that. Yeah, that's certainly the case. But servos in your speed racing things, how many servos do you have on your surface? No, your quadcopter drone racing, you don't have any servos at all. Really, you don't do this actually just for RPM control? You don't have any? I thought these speed racers have variable pitch.
Yeah, they do. You bring the balance faster. That's it. You have full control just by.
No, I understand that, but you have even faster control if you have actually very low variable pitch blades. And I've seen quite a lot of speed races that actually have that. But you're not flying those?
I haven't seen those at a racing race. No, like professional racing. No.
Okay, cool. That's interesting.
I've seen racing quads using variable pitch.
Plenty. I can send you some links to those.
Like quadcopters,
yeah? Yeah, that's right.
Okay.
Sure. Well, even for a quadcopter, you have still a much faster reaction if you can actually just change the pitch of your blades rather than actually have to change the RPMs. And I would have thought for. Say again?
Yeah, you get faster yaw, but everything else, I don't think you get that much benefit out. I mean, you get 3D blades, which are then over 45, and so that you can get inverse thrust. So yeah, do something with that.
Sure, that's just super inefficient, but yes, that's.
Cool. I mean, motors are so good these days, and batteries are so good. You just,
Okay.
you get thermal thrust out of 3D blades.
maybe the torque in the current race drones is so high that you can actually compensate for that. Yeah. Okay.
Getting into the right cruise will leave the amount of power. Like I use 4-inch props. You go up to a 5-inch prop, and like you blip the throttle and you lose sight. Like you hit the clouds.
Sure. And they're also formed in a way that you can actually push them down as well, with what you call inverse flying. But you also, if you want to actually come down with anything faster than 1G, you actually have to push down. But you're not coming down with anything faster than 1G. No? Really? Okay.
Well, because typical races only have, like they're designed, they've got blades like this so that you can get the most thrust going up once you've gone up.
Sure.
Unless you do this and throttle, which you can't do, you can turn upside down.
I was always annoyed by these things when I try to get these things down. Because with my helicopters, I just tell them to come down and go, and I can control this in both directions at any speed I want. I'm not bound with a 1G acceleration. With a RPM-controlled drone, of course I can shoot them up pretty quickly, but then I have the feeling like I'm actually sailing them down. Just shoot them up, because it's just 1G coming down.
Yeah, well,
and for a helicopter pilot, 1G is actually not much. So.
Well, yeah, you hit the throttle, you go up, you take the throttle off, and just keep going.
Yeah, of course you have the momentum up first. You have to actually wait until it turns around and then falls down.
Yeah.
And there's a reason why I think I crashed my first 5 quad drones straight out, because I couldn't imagine that I have so little power in the opposite direction to catch for that. So you actually let them fall down. And of course, if you let them fall down from a larger height, it's quite a while.
Yeah.
And
at a low speed, you hit the bottom, you got to learn to account for that.
And from a helicopter, you can just let them free fall if you like to, or you push them down. And on the last meter, you just get the pitch in, and on the last meter, you go, and then set them down. That's how you do that in our professional helicopter pilots, full-scale pilots. I also trained to land their craft called auto-rotation, as you know, so that every full-scale helicopter can be put down without any engine. Most people don't know that. But you even need to have regular training as a helicopter pilot that you can land your helicopter without engine. With the quad, that's not good. Exactly. But there's just, at least when I was still flying these things, the quad things, it just took a noticeable delay until the engines came up from still stand, until you actually get enough thrust to do that.
Not these days.
Okay, good.
Motors got way better.
Okay.
It's phenomenal how much power you can achieve whatever the battery.
I never had enough buffer between the point when I decided to slow the thing down and the motors were spinning up. So it was usually me trying to decide that now would be a good time to counter thrust. And then the motors decided slowly to spin up, then the thing crashed, and the motors slowly began to actually gain momentum. It was more than... Okay.
I'm really impressed with the state of quad motors now. They're tiny, really matter.
Okay. Well, the fact that you do racing without collective pitch blades speaks for it.
Just fly along with this.
Okay. Sorry, I got a bit distracted. How many servos do you have on an actual flight surface?
Just one thing.
No, you have. This is something you can actually replicate. Yeah, no, that's the flight surfaces themselves. But the question is, how many servos, how many hydraulic devices or pneumatic devices you're actually attaching to each of them, and you just usually replicate them. You have a whole row of them. So if any of these pneumatic devices actually leaks or fails, you can still move the surface. And this also goes for the rudder. So the rudder also has always multiple points to still move it around if one of the activators are actually failing. But the single point of failure which is still left is the actual surfaces, wings, rudders. There's some point which you can no longer replicate. But up to that point, pretty much everything in your devices, you can put multiple instances in there. Of course, you put multiple instances in there, the thing gets more complex, gets heavier, needs more power, so it has again possibly a lot more points of failure because it's a heavier, more complex system to start with. So next thing we are defining is triple modular redundancy or n-modular redundancy. That's the common industry term for any system where you have a default multi-hot standby redundancy system. Usually you start by triple modular redundancy. You have three systems which are going side by side, and you have to connect them so that you suggested a voting system. How do you do this electrically? Logical gates. Yeah. Or you have a big computer which takes the messages from everybody and then runs an algorithm which.
But you might also have it where they're all on a network and they send the results to everyone else. So
yeah.
computers have these are my results.
Yeah, but if your network fails, what do you do then? So it's not only the devices which actually produce results, it is also the network in between. And in airplanes, for example, you can just rip out cables anywhere. So not only that you can take an axe and go to the next flight controller and ram it in there, you can try this on your next flight, nothing is happening. I mean, there is something happening, but it's on a police matter kind of basis. But for the flight controller, nothing is going to happen. You can just take an axe and ram it straight to the next flight controller you find in this airplane. You can also dismantle the side of your seat and get all the cabling. And all the cabling which you find in this one spot, you can just randomly rip out. Again, it will have side effects of different nature, but your flight will not be interrupted from that. How do you do that? What kind of bus system is that? What kind of network is that? Yeah, so you have to be able to logically and electrically isolate these kind of flaws. So a system which would, for example, be prone to short circuit with something would be quite disastrous. You have to be sure that by ripping stuff out and or putting cables together which you find someplace, your system is not short-circuiting. You need to have enough protection for all of that. And the rest of your network can easily take over this load, regardless of where you rip out cables in those systems. And the interesting question is always, how do you connect them? The voting node, the voting system, you can always just replicate blindly hardware and devices, and they all produce parallel signals. But at some point, these parallel signals have to be communicated to your flight surfaces. They have to be combined into one signal at some point. And you're right about your logic gate idea. You try to do this as primitive as humanly possible, because that's by definition a single point of failure, which is unavoidable. Getting all of the signals from an n-modular redundancy system into one control output is by definition a single point of failure, and that has to be very solid and simplistic to do that. Okay. On Monday I would like to design actual n-modular redundancy systems and discuss practical systems. And next time you may look at your ticket and may have possibly some preferences for some airplane models over others, because you may be more knowledgeable about which models have what form of redundancy in them. You want to know that? Yeah? I cannot undo that. Right? It's like my lecture about typography and typesetting and things like that. Once you know that, you can never unsee that. You can never get this out of your head again. Okay.
Who do you fly with?
Say again?
Who do you fly with?
What I fly with?
Yes. Do you design your own systems?
I I think I'm still on record. I shouldn't say that.
Is that what the helicopters are for?
Yeah. All right. Enjoy your work Saturday, unfortunately.
I'm getting to finish tonight.
Yeah. All right.
Thanks, Eva. Enjoy.
Yeah, you too.